All right, so as you can see, Cranberry and I stepped into a small space-time anomaly, and it is now nighttime, and I have a cup of tea. So now that we're back, we're going to talk about a specific category of reconstruction attacks that we can analyze mathematically and say nice things about called linear reconstruction attacks. These were introduced in a really beautiful and influential paper by Irit Zinur and Kobi Nissim in 2003 that really inspired a lot of what we're going to talk about in this class. So the reason we're going to study linear reconstruction attacks is a couple things. So one is that this is a nice mathematical model for linear reconstruction attacks that lets us prove that the reconstruction attack will be successful. Another reason is that reconstruction attacks that are linear are often robust to noise in the answers we're given. So we can talk about specific trade-offs between what kind of statistics we're answering and how many and how much noise is in them. And that's going to have implications for how much noise we need to achieve privacy later in the course. And the last is that linear reconstruction attacks are reconstruction attacks we can carry out efficiently with polynomial time algorithms based on linear programming. So in the examples we saw before, we did sort of more kind of ad hoc reasoning about reconstruction, and now we're going to see something a little more systematic where we can write down a nice mathematical model. So to start, let me describe the model. Whoops, I guess I don't know where my face went, but that says a model for reconstruction attacks. So I'll talk about a model, and I'm going to talk about sort of where the model comes from. So to start out, imagine we have a data set like the one on the left. So it has a number of attributes that are identifying, like name and the postal code where you live, and your age in years, and your reported sex. And it also has a sensitive attribute that we think of as kind of a special bit. So for today, we'll think of it as a bit, and it'll just be something like has disease. Okay, so some disease. And what we're going to do is think about this data set as having two parts. So we'll think about it as having identifiers. These are information that is maybe not on its own particularly sensitive, but can be used to identify you, and a secret. And we'll assume that the identifiers are known to the attacker and unique. Okay, so both of these assumptions can be relaxed, but it'll just make our life easier if we think of these as known. So an attacker knows this information about you, and unique. So nobody has the same first name and lives in the same postal code and has the same age and years and sex. Okay, on the other hand, we'll think of the secret as unknown, and the attacker is trying to reconstruct this secret. Okay, so the question phrased in this model is, can an attacker who knows attacker who gets the identifiers and some statistics involving the secret reconstruct the secret? Right? And in particular, we want to know if the attacker can do this given noisy statistics. So not exact statistics, but noisy statistics. So we want like a simple model where we can kind of strip away some of the complexity. So what we're going to do is we're going to think of the database as having n rows, and each row is just going to have two parts. It's going to have the public identifier z and the corresponding secret bit s. Okay, so what do we have here? Zi lives in some set z, and si just lives in 0, 1. And in this particular example, you can think of z as representing, say, a tuple that contains like a name, a postal code, an age, and a sex. But it's really not going to matter what's in the identifiers for the rest of the lecture. It's just going to matter that it's some kind of uniquely identifying information that's known to the attacker. And So that's going to be our model of a data set. And now we're going to throw away kind of the real data set, and we're just going to work on this kind of simple model on the right. And we're going to see, can an attacker reconstruct the secret bits S, and what do they need to do it? So now we just have this data set on the right. So what kind of statistics are they going to ask? Well, we're going to consider what are called count statistics. And these are also sometimes called linear statistics for reasons that will become clear. So what is the statistic? So it has the following form. We're going to count the sum over all of the individuals in the data set, so j equals 1 to n, of the following thing. So we'll have some function phi that takes in zj and output 0 or 1 multiplied with sj. Okay, so phi j is some function that maps the identifiers to 0 or 1. So how can you interpret this funny query? Well, when is the jth term in the sum 1? It's 1 if and only if the secret bit is 1 and phi of zj is 1. So for example, phi could be something like, is this person over 40? And it outputs 1 if the person is over 40 and 0 and otherwise. Example, phi z equals 1 if z over 40, 0 otherwise. In which case this query would ask, how many people in the data set are both over 40 and have the disease? Okay, so another way to think about this is as asking for, among the subset of people in the data set who are over 40, how many have the disease? And phi is how you specify the subset. Okay, so this is the kind of statistic that we want to answer. And the reason these are sometimes called linear statistics is because they can be written as a dot product between two vectors. The first vector is the one that applies phi to all of the identifiers z1 through zn. And the second vector is the vector of secret bits. Okay, so this is the dot product. And as a result, we can give this vector a name. We can call it f in 0, 1 to the n. And this vector is s in 0, 1 to the n. And each query specified by some function phi is just getting a dot product between s and some different vector. Okay, so the reason that these are called linear is because they're dot products with the secret vector. Now, one thing that might seem a little strange is that the definition of queries has sort of baked in the idea that one of these columns is special, it's a secret. So I want to make a clarification that this is not something we think of as being inherent in the way the data set is constructed or even in the way the queries are constructed. We just think of the secret as being special in the viewpoint of the attacker. So really the data set is just a bunch of information, but from the attacker's point of view, they're trying to reconstruct the secret. So we're going to focus attention on queries of this form. Okay, so we're going to focus our attention on queries that have this form, that they ask among people in some subset of the data set, how many of them have a secret bit set to 1. But these can arise in other ways, and maybe I can clarify later some examples. Okay, so these queries are linear. And another thing to note about these queries is that the answer is some number between 0 and n. So the answer is between 0 and n, and what that means is that if I'm going to get the answer up to some small error, then it better be that the error is significantly smaller than n, or else it's not really telling me anything. If if I tell you that one of these queries is 0 plus or minus n, that's not really giving any information. But if I say that it's 0 plus or minus n over 100, that is giving you some information. Okay, so an answer is non-trivially accurate if the error is significantly smaller than n. And if the error is kind of close to n, you're getting essentially no information. Okay, so these are the type of statistics we're going to answer. And what we're going to show is that if I give you enough of the statistics like this, then an attacker can recover essentially all of the secret bits. And the last thing I want to say is that notice that if the identifiers are unique, then for any vector f in 0, 1 to the n, I can construct a query that has that vector, where that vector arises. So what I mean by that is, okay, so for every f in 0, 1 to the n, there exists phi mapping the identifiers to 0, 1 such that the vector f is equal to phi of z1 up through v of zn. Okay, so how do I do that? Well, if f were, for example, 1, 0, 1, 0, then I can set phi to be equal to 1 if, phi of z to be equal to 1 if z is equal to z1, or z is equal to z3, and 0 otherwise. Okay, and you can check that if I apply phi to all of the public identifiers z, I'll get exactly the vector f. Okay, there might be other ways to specify this query, but what we're going to do is we're kind of going to ignore how you would choose the phis, and we're just going to think about choosing the vectors f. So we're just going to think about which inner products do I want to compute with the secret vector in order to reconstruct the secret vector. And we're going to rely on the fact that as long as the identifiers z are unique, there's going to be some way that I can choose the query phi in order to obtain those inner products. But we're not going to think right now about how to do it. At the very end of the next lecture, I'll talk a little bit how in a practical setting, you can come up with actual queries of the form we talked about that will that will have the vectors you want in order to do reconstruction. So we'll talk a little bit about how this would come up, but from now on, we'll just think about choosing queries f. So okay, so f1 up through fk for some set of vectors in 0, 1. Those are going to be our queries. We're going to sort of, so I told you the story of where they come from, but we're now just going to think in terms of choosing these vectors. All right, so let's see a first example of how we can choose the queries in order to obtain a reconstruction attack. And what we're going to show informally is the following claim, that you can't hope to answer all count statistics with any non-trivial accuracy guarantee. So what I mean by that is if I'm going to answer all count statistics on a data set and the noise is going to be significantly smaller than n, then an attacker is going to be able to recover essentially all of the secret bits. Okay, so they'll be able to recover the secret bits of all but a very small number of people in the data set. So first, what is the attack? Like, what are the queries? So let k be 2 to the n, And for every vector v of length n, define a query f sub v equals v. All right. So what do I mean by that? I mean, if v is 1, 0, 1, 1, 0, then we just choose the query so that it is exactly that vector. So we construct some phi so that we get exactly this vector as the query. All right, and my set of queries is going to be all of these things. So my set of queries is going to be f sub v for all v in 0, 1 to the n. So I'm asking 2 to the n queries, and I'm basically asking every possible query I could ask given the n public identifiers I have. Okay, so now that I've restricted attention to this particular type of query, I'm actually just asking every unique query that I can possibly ask, or every distinct query I can possibly ask. All right, so that's the set of queries. There's 2 to the n of them. It's just all the queries. So I'm going to get the inner product of S with every vector. All right, now how am I going to reconstruct? Well, okay, so how am I going to reconstruct? So I get answers, which is a collection of values, one for each query. So for every vector v, I get an answer to the corresponding query. And what it satisfies is that for every vector v in 0, 1 to the n, v dot s is at most alpha n from the true value, given the secrets I have. Okay, so I get accurate answers to all these things. And that's great. I get accurate answers to all these things. And notice that there's this accuracy parameter alpha, which is somewhere between 0 and 1, and that's because I said that if the error is as large as n, this is not interesting. I could just answer 0, I'm not getting any information. If alpha is 0, then I'm getting exact answers, and so alpha is some number between 0 and 1 that kind of says what is the error as a fraction of the size of the data set. Okay, so those are my answers, and then to reconstruct, what I'm going to do is choose any candidate set of secrets that are consistent with the public information, or sorry, consistent with the answers. And what does that mean? Well, it means that for every query, S tilde should plausibly be the correct set of secrets, which means that v dot S tilde minus the answer to that query has to be less than alpha n, right? Because the correct vector of secrets would satisfy that guarantee. So if the vector S tilde doesn't satisfy that guarantee, it can't be the true vector of secrets. So I'm going to choose any vector that cannot be ruled out based on what I know about the true vector S. All right, and one observation is that this takes 2 to the n time. So we'll talk in the next lecture about how to make this efficient, but for now we're not going to worry about how to make this efficient. We're just going to assume that you enumerate all the vectors S tilde, and we're going to just figure out how accurately you can reconstruct, but not worry about reconstructing in polynomial time. the other thing to note is that there's always at least one such vector s tilde, because the true vector s satisfies this property. So we're never going to search through all the vectors s tilde, and we're never going to search through all the vectors s tilde and find out that there is no feasible choice. Okay, so there's always going to be some vector that's consistent with the information we have, because we know the true vector of secrets is such a thing. All right, so a reconstruction attack. And what are we going to prove about this attack? Well, what we're going to prove is the following result. We're going to prove that, sorry, just doing a little bit ahead. We're going to prove the following theorem. So we'll prove that if all 2 to the n counts are within at most alpha n error of the true value, then s and s tilde disagree on at most 4 alpha n coordinates. Okay, so what does that mean functionally? So first of all, when I say disagree, what I mean is that s tilde gives the wrong secret bit for at most 4 alpha n people. And what that means is I'm recovering essentially all of the secrets if alpha is small. And let's just look at some special cases of this. So first of all, if alpha n is 0, so if I have no error, then this says that s and s tilde do not disagree at all. I recover all the secrets accurately. Okay, so if the error is nothing, then I get exactly the secret bits back. So maybe that's not surprising that if I get exact answers, I should be able to recover all the secret bits. We already talked earlier about examples where if I can come up with counts that are accurate exactly, I can just read off the secret bits. On the other end of the spectrum, suppose that alpha is like 1 over 20. Okay, so if all the answers are accurate, if the error is at most 5%, meaning all the answers have error at most 0.05 n, okay, so I get like a reasonable estimate, not even a very accurate estimate. I can be off to like 5%. Then the reconstruction will get at least 80% correct. Okay, so I'll recover at least 80% correct. Now, there's one very important thing I want to say about this result, which is that notice that in the theorem, there's no assumption on s. So I get s correct for any s. And what that means is that I'm really doing something that I can only do because I received the statistics and because your data was included in those statistics. So I want to make this point. So let me zoom down. So this theorem works for every vector of secrets S. And why is that important? Well, first of all, what it means is that it works even if the secrets were like completely random. And if the secrets are completely random and I don't give you any statistics about them, then the best an attacker can do is guess them. Okay, so note an attacker who gets no statistics can only guess 50%. Okay, so what do I mean by that? I mean, imagine that everybody just flipped a coin for their secret bit, and I don't give you any statistics about the data set. I just ask an attacker to guess whether my coin came up heads or tails. Well, they're only going to get it right 50% of the time. Okay, but because I gave some statistics out, the attacker can now get them right 80% of the time. So they're really doing something that is recovering a lot of information about the statistics that they couldn't be getting if they didn't have, recovering a lot of information about the secrets that they couldn't be getting if they were not given these statistics about the data set. Okay, so the attacker can't do this without the statistics. Okay, so that's important. And secondly, maybe in the real world, the disease only occurs among 5% of people. So if I just answer nobody has the disease, I'm actually accurate to within 5%. Okay? But because it works for all statistics, I'm not just using prior information that the disease is rare. I'm really using, I really like, the attack has to work. Okay, so first of all, I want to say that, the attacker, because it works for all secrets, the attacker should kind of, in the worst case, only be able to get half the secrets correct, but they're getting 80% correct. So they kind of, something is really being communicated to the attacker through the statistics. The second thing I want to note is that the attacker can't do this without your data in the data set. Okay, so what I mean by that is if you had just not put your data in the data set, if we just cut your data out and your secret bit is just a coin flip, then an attacker who only gets information about people other than you cannot guess your coin flip. Okay, so they're really learning something about you because your data was included in the data set and included in the statistics, and that's really important. So they're not just using some background information that most people don't have the disease, and therefore whether or not you're in the data set, they know they think it's likely you don't have the disease. They're really guessing something about you that's happening only because your data was included in the data set. So you putting your data in the data set and those statistics being released together caused the attacker to learn something about you. So we're going to revisit this point a lot when we talk about how to correctly define privacy, but what I really want to emphasize is that a reconstruction attack is something that really shouldn't happen unless the statistics revealed a lot about the secret bits. The attacker sort of can't do the reconstruction by accident. They're really only doing it because a lot of information was revealed about the data set itself. All right, but I'm going to move on. So let's focus now on how to prove the theorem. So I think a lot of these points will become hopefully more clear as the class goes on, but I want to focus now on just proving the theorem. And let's just get a little intuition for the theorem before we go on and prove it. Whoops. So I want to give you some intuition for this theorem. So suppose that S tilde and S differ on a large number of coordinates. Okay, so these differ on a number of coordinates, and in particular, there's a number of coordinates, 40% of the coordinates, where S is 0 and S tilde is 1. And I want to claim that there's some query that will tell us that S tilde is a bad choice for the vector S, and therefore will not be what we choose by the reconstruction. So that query is just going to be the query that puts ones on all the red numbers, or on all the red coordinates. So the query that's going to do that is just the one that's going to put ones on those first two coordinates. And why is that query useful? Well, that query applied to S tilde is 2, and that query applied to S is 0, because these red coordinates are exactly the ones where S tilde is 1 and S is 0. So the difference between the answer to the query on S tilde and the answer to the query on S is exactly the number of coordinates where Sj is 0, S tilde j is 1, number of coordinates j. Okay, so if S tilde and S are very different, there's kind of two reasons they can be very different. One of them is that there's a lot of coordinates where S is 0 and S tilde is 1. And if that's the case, then there's some query V that has a large answer on S tilde and a small answer on S. So let's draw a line and let's plot these two answers. So here's V dot S, and here's, whoops, and here's V dot S tilde. So here's the answer to this query for the two secrets. And they're very far apart. And we were given some answer A sub V that was fairly close to V sub S. And by fairly close, what I mean is that V dot S lives in an interval of length, 2 alpha n around A sub V. Okay, so we were told some number that's close to V sub S. And what that means is that the only choices for S are the ones that are within this interval. Okay, so any S tilde outside of here cannot possibly be the correct choice. Right, so this one cannot, like S tilde cannot be the vector S, because the answer to this particular query told us that this thing was too far apart. All right, and that's going to be true whenever the number of coordinates on which S is 0 and S tilde is 1 is really big, because that's, the bigger that is, the further apart the two red dots are, and that's what's going to push one of the red dots outside of the purple range. Okay, so each query kind of eliminates some set of S tildes, and in particular, if S and S tilde are very different in this way, there's going to be like one particular query that's going to sort of catch that difference. So let's see if we can turn that into a proper proof. So remember, here's the theorem we want, that if all 2 to the n statistics are answered with error at most alpha n, then S and S tilde differ on at most 4 alpha n coordinates. So here's the proof. So let's define 2 sets. So S01 is the red set from the previous slide. It's all the coordinates where the true secret is 0 and the S tilde is Sj. And we'll also define the symmetric set that says all the coordinates where the true secret is 1, but the reconstructed secret was 0. And what we want to prove is that if S tilde is far from S, then it can't possibly be the reconstructed secrets. So let's assume, for the sake of contradiction, that S and S tilde differ on more than 4 alpha n coordinates. Well, that implies that one of these 2 sets is bigger than 2 alpha n. Okay, so there have to be either a lot of 0 to 1 flips or a lot of 1 to 0 flips. One of the 2 things has to be true. So in the last slide, we said there were a lot of 0 to 1 flips, but it could have been the reverse. All right, and the argument that we used in the last slide basically said that if this is true, then there exists some vector v, so some query, such that the difference between v dot s tilde and v dot s in absolute value is at least 2 alpha n. And the reason that it's now in absolute value is because last time we sort of only considered S0, 1, but the symmetric case would give you a negative. All right, so there's some query where the correct answer to the query on S tilde is very different from on S itself. So what does that mean? That means that by the picture I drew last time, it means that the difference between v dot s tilde and the answer we got to that query is at least 2 alpha n minus the difference between the answer we got and the answer on the true secrets. And because we know that the answer on the true secrets is accurate to within alpha n, we know that overall, this absolute value is at least alpha n. Okay, and this is, by the way, something called the triangle inequality. If you don't see it, it might be worth just working out. But this is just a way of expressing the picture I drew on the line. So it says that the error of v dot s tilde with respect to a sub v is equal to the actual difference between v dot s tilde and v dot s, and the difference between the v dot s and the a and av. Okay, sorry, it's easier if you draw a picture. All right, so, but if that's the case, that means there's some v that was in our set of queries, because every vector v is in our set of queries, right? So important thing is, because every v in 0, 1 to the n is in our queries. Okay, so every vector v is in our queries, so in particular this v is, and that means that there's some v such that v dot s tilde minus av is strictly greater than alpha n, and that means that s tilde was not chosen by the reconstruction attack. Right? And if it was not chosen by the reconstruction attack, that means that something went wrong here. It must be the case that s and s tilde do not differ on more than 4 alpha n coordinates. All right, so that's the proof. This proof is really just sort of a slightly more precise way of describing the intuition I gave you on the last slide. So let's just wrap up. So we proved the following theorem about our linear reconstruction attack. So we came up with a model where we can ask these queries that give us an inner product between some vector we know and control and the secret vector s. There's 2 to the n such inner products, the way we define them. And if I answer all 2 to the n inner product queries with error smaller than alpha n, I reconstruct the secret vector to within 4 alpha n. So I get 4 alpha n people, all but 4 alpha n people right. And what does this really mean? So it means that if the error is much smaller than n for all queries, then I reconstruct almost n secret bits correctly. Okay, so you can prove things like, if I give all the answers are correct to within plus or minus 1%, that would be alpha equals 0.01, then I reconstruct 96% of the bits correctly. And if I reconstruct with error, say, square root of n, then I'm going to get n minus square root of n people correct. So the number of people that I'm wrong for is going down kind of proportional to the error in the queries. Okay, and this theorem has an important interpretation. So even though this attack is computationally inefficient, even though we're not reconstructing exactly, the way I think to interpret it is to say that we can't hope to prevent reconstruction if we don't put some limit on the number of statistics we reveal. Okay, so even this statement is sort of non-obvious. We're taking this type of statistic that seems very benign. We're just counting the number of people with the disease in certain subsets. We're allowing a fairly large amount of noise, and yet we're saying that if we don't put some limit on the number of statistics, then we can't release any answers that have sort of any reasonable accuracy guaranteed. They have to have error that's huge, kind of very close to n. So even that statement is kind of non-obvious, and it's something that's very important that comes out of this work. Of course, 2 to the n statistics is an enormous number of statistics. If we have a data set of size 100, You know, we don't really need to answer 2 to the 100 queries about it. So what we'll see in the next lecture are reconstruction attacks that use many fewer queries and can be made computationally efficient. But what we'll pay for that is they'll have to be given answers that are significantly more accurate. So we won't be able to reconstruct if the error is as large as, say, n over 100. We'll only be able to reconstruct when the error is somewhat smaller, about root n. And that number is going to actually have sort of a fundamental interpretation as to why. So that's it for this lecture, and I will see you in class.